open the current slide. And as soon as, okay. I'll try to remember to go back and do this. I think we're going to have the most room there. All right. A couple of announcements. Nothing all that critical. I just wanted to say again, Alabama A&M has started a Norse program. If anyone's interested, please consider that. And this is something happening today. So you're about the only class that's going to get this announcement. Just got it, printed it this morning, okay? A visiting artist lecture, Edward A. McLeod. He'll visiting guest artist for Black History Month, Edward A. McLeod, whose artwork is on display in both libraries on both Birmingham and Bessemer campus. We'll be discussing his artwork with students today, Monday the 25th, from 12 to 1:30. This is over in the Thelma Catlin Auditorium on the Birmingham West Campus. Now that's in Building D. That's the library building. And if you can't find the auditorium, don't feel bad about it, because no one can find the auditorium. Ask at the library's desk. If you don't know where it is, ask. They'll point you right around the corner. It's just not well marked at all, but it's a nice little auditorium there, and it's easy to get to right from the library, right next to it. So that's today, Thelma Catlin Auditorium, Bessemer State Community College, Birmingham West Campus, from 12 to 1:30. And if you need any further information, Mrs. Blankenship is the art instructor who has arranged this. I have her email. You don't have a lot of time, so you can get there from here in plenty of time, but you don't have a lot of time to email her, is what I would say. All right. Taylor, right? Okay. Now, another thing I was supposed to do this morning, and I forgot to do it, was call roll from the permanent roll, official roster. All of you are on it anyway, so I'm not worried about that. The one person who wasn't on it, I've already spoken with, so I think that's probably been taken care of. So anyway, I never did count. 2, 4, 6, 8, 2, 4, 6, 8. Got it. Okay. All right, where we're picking up today, any questions on anything we've done so far? Well, that was one announcement, the art thing. Let me give you, I think there's 3 more in a row that only bothers if you're planning to try to catch me on a Friday. This coming Friday, March 1st, I have a dermatology appointment at Kirkland Clinic at 9:15. Now, I haven't decided yet whether I'm going to go to the Birmingham campus at 8 when I usually get there, a little before 8, but then leave by 8:45 to go back to the Birmingham clinic, and then once the appointment's over, then go back to Birmingham campus. No, I won't be on the Birmingham campus from 8:45 until probably 10:45. That's just a guess now. I don't know how long the appointment will take. So don't plan for me to be there. I may be there before 8:45, 8 to 8:45. I'll definitely try to get there after 10:45, depending on what time the appointment's over. But technically, usually only there till noon, though I'm usually there after noon for a while. So, just in case you're looking for me on the Birmingham campus this Friday, from 8:45 till about 10:45, don't figure for me to be there. Before and after, I may or may not be planning to be, but I'll just have to see how it goes. Because it may make more sense for me to work from home and not waste the half hour to 45 minutes driving to campus and then a half hour, 45 minutes driving back to the appointment. I might be able to get more work done just at home. So I'll talk with my boss and see which he would prefer me to do. Okay, but I will go after the appointment to the Birmingham campus. The following Friday, I have an articulation meeting in Mobile. So I'll be leaving something like 6 in the morning to drive down to Mobile for a 3-hour meeting and then driving back after 3 and getting home probably around 9 o'clock or so. So I won't be on campus at all the following Friday. I will be there shortly this Friday. The Friday after that, I have an eye appointment right next door, across the street at the UAB West Hospital. Sorry all these things are coming at once, including Frank is coming. I mean, that's fine for him to be here. Okay. And that will be, I think the appointment is 8:15, so more than likely I will just stay on this campus because usually they dilate your eyes and all that kind of stuff. I'm sure they will. And it'd be safer for me to just walk across the street and stay here in this building at least until the dilation goes down and I feel comfortable enough to drive. So you can drive. They give you the big heavy shades, but I'd just as soon stay here unless something else comes up and I have to go over there. So it's that 3 Fridays in a row I will be somewhat out of pocket, and that almost gets us to spring break, so I'll be here then, though. I mean, partly. All right, any questions before we get going? Okay, sorry about all that. Let's do example 8, the last example left in chapter 2 that we're going to do. This is on page 148, bottom of the page. Finding a tangent line to a graph. Okay? Find the tangent line to the graph of, let me get my pen set up, sorry. Got to do that. Okay. X squared times x squared plus y squared minus y, no, I'm looking in the wrong place, is equal to y squared, okay, at the point root 2 over 2, root 2 over 2. Okay? As shown in the figure. And we don't have the figure on the slides yet, so I will draw it quickly. No, I don't draw anything quickly. I'll try to do a rendition of it, a gross rendition at that. It looks like 2 kissing parabolae, okay? Except they're not parabolae. They have, these are called the kappa curve, and I think I mentioned before we left last week that Isaac Barra was one of the ones who did a lot of work on this. And I guess we would have known Isaac Barra maybe because of this, but what he's most famous for is being Isaac Newton's advisor and instructor. Okay? And he had been holding the Lucasian chair of mathematics at Oxford University, and once he had Newton as a student, he gave the chair over to him. He said, "This guy has passed me," and kept going. So I find them a pretty honorable character to do something like this. So this has vertical asymptotes at plus and minus 1. And it's it's not drawn very well. It looks like like I said, 2 kissing parabolae, only they're not parabolae. Parabolae don't have vertical asymptote. So in that sense, they look a bit more like a secant or a cosecant curve, more like a secant because its center is even, but that's not it either because it's never between minus 1 and 1. So just curves like that. Now, before I do anything else, I want to make sure that point root 2 over 2, root 2 over 2 is indeed on this curve. Okay? And how we do that, just plug it in, plug it in. What is root 2 over 2 squared? Anyone know? Or can figure it easily? Not quite. Square it. That would be square of a square root would be 2. Square of 2 would be 4. That would be 1/2. Okay. So this would be 1/2 times 1/2 plus 1/2 is equal to 1/2. Is that a true statement? 1/2 plus 1/2, pull out the calculators. What would that be? 1. 1 times 1/2 is 1/2. Yes, that point is on the curve. Okay, so that part we won't have to do. They didn't give us a red herring or a whatever they call them. That would be. So somewhere over here at root 2 over 2, which is about 0.707, and 0.707 here, that point is on the curve. And what we're looking for is the equation of the tangent line at that point. And it's sort of important to get that part down because you see, technically, this is not a function, is it? It's an equation. Why is it not a function? Why do I make that bold assertion? It's not a function. Say again? It fails the vertical line test miserably between -1 and 1. Okay, so therefore, not a function. But it is an expression, it is a curve, and this is called the kappa curve, by the way. Okay. So how are we going to find a tangent line? What do we need to know a tangent line? Or any line. The equation of a line. Slope would certainly help. What else will we need? Slope alone will not give us an equation of a line. A point. Well, we got a point, don't we? Yes. Okay, what's the point? There it is. Okay. And we need a slope. How do we get the slope? Take a derivative, of course. So let's take the derivative of both sides of this equation. They rewrite first. And I guess that's okay too. I really don't see the point because they've still got to do implicit differentiation anyway. Let's just do it as it is. On the left-hand side, what are we going to have to use? Not yet. We will. So I got product rule. So let's do the product rule. How does that go? Say again?
X squared.
X squared, okay, that's the first, times 2x plus 2y, what? Y prime. Okay, he's writing it shorthand. He's really lazy. Okay. Plus well, wait. I shouldn't have done it too fast, huh? Oh, okay. Yeah. Okay. That's okay. X squared plus y squared. Sorry, I buzzed you too soon. Times 2x. Okay. I would have put that in front, but that's okay. Next is equal to 2y prime. All right. Now what? What a mess. What do we do next? Anybody? Help me. Say again? Okay, divide by 2y. Okay, that I want to hold off doing that yet. And part of the reason is this term that we're going to have here won't have a 2y in it. This one will, but none of these terms will. So I want to hold off doing that quite yet. Anyone have another suggestion? Ultimately, we are going to do it, but not yet. What do we need to do first? Distribute. Let's distribute first. Get all the terms as they're going to turn out. And then we'll deal with isolating the y prime. Okay, so what do we get in the first term here? 2x cubed. Next. Plus. Second. 2x squared y prime. See, we're going to have to divide by more than just that. Okay. Plus 2x cubed again. Plus 2x y squared. Is that what you said? I hope so. All right. Is equal to 2y prime. Now there it looks tempting to divide by that, but you see we've got this other y prime. We need to get those together first, then we'll divide. Okay? So basically what I'm saying is let's get everything with a y prime on one side and everything without a y prime on the other side. Now which way you want to go with what then? Second? Yes, let's subtract this one from both sides because everything else is over here anyway. So we're going to do a minus 2x squared y prime minus 2x squared y prime. And these will go away. So we have left, I'm going to switch sides. Is that okay? I'm also going to undistribute, if that's okay. So starting with this side here, I'm going to separate out my coefficient. Now, if I'm skipping too many steps, tell me. So we have 2y minus 2x squared y. So see that? Minus 2y, or 2y would have been a great thing to get rid of, but you still have something left here, times y prime. Now, see what I did? Combining those together, 2y prime minus 2x squared y prime would be 2y minus 2x squared y times y prime. Okay? That's the left, what used to be the right-hand side, now the left-hand side. And what's left over here is a 2x cubed. And frankly, it would have been good to get rid of the 2's anyway. I wish I'd have listened to you. Okay, 2x cubed plus 2x cubed would be 4x cubed. Let me just write it that way. Okay. 4x cubed, that is a cube there. It's ugly, but it's there. Okay. Plus 2x y squared. X y squared. Okay. I think I've got everything there now. Now, let's get rid of the 2's. Get rid of that, get rid of this. Make this the 2 like it was before and get rid of that one. Sorry about that. That's ugly as all get out. But we'll clean it up in the next step. Everybody see that? We did have a 2 in every term. I hadn't been paying close enough attention. We should have divided out the 2 anyway. All right, so what do we have left? We want to isolate the y prime. How do we do that? Divide by this coefficient here. Okay, so if it's okay, I'm going to do it in one big step here. Y prime is equal to, the numerator part over here will be a 2x cubed plus xy squared. I don't need the parentheses, I don't think. You might if you're using a calculator later, but I don't need it for writing this down. Divided by y minus x squared y. Did I do it right? All right. Now is the plug-in time. Wait, what do we plug in? Yeah, and that's root 2 over 2 comma root 2 over 2. So everything's root 2 over 2. So what does this first term become? 2 times what's root 2 over 2 cubed. We already know what root 2 over 2 squared is. Remember that? 1/2 times another root 2 over 2. So that would be a root 2 over 4, wouldn't it? Okay. All right. Plus, this is a root 2 over 2, and 2 more root 2 over 2s. That's another root 2 over 4. Am I not correct? I think that's right. So that gives me 3 root 2s over 4. Okay? Denominator will be a plain old root 2 over 2 minus, and there are 3 of them again, so that's a root 2 over 4. Okay. Now, something is not coming out right, I don't think. How's that? No, it's fine. It's fine. Okay, sorry. Thinking badly. Okay, so what do we have here? In the numerator here we have 3 root 2 over 4 divided by, and if you made this a root 2 over 4, which everything else is, you'd have to have a 2 here, so this would be a 1 root 2 over 4. And it's pretty obvious that goes out. Looks like the slope is a 3, doesn't it? Yay or nay? Yeah, that's what they got to. Now, they went about it a little differently, but we got a 3. Okay? So what do we do with that? The calculus part's over with. The rest of it's math. Okay? Algebra, whatever you want to call it. Okay? Point slope formula, how does that go? I can't write well, but
equals 3 times x minus 2 over 2.
All right. Now, let's see, that will be y minus root 2 over 2 is equal to, again, distribute 3x minus that good old 3 root 2 over 2. We keep seeing the same things almost over and over again. And let's add another root 2 over 2 to both sides. Okay, but this time it does simplify nicely. Y is equal to, these go away, 3x minus, oh no, it was a minus 3 root 2 over 2 over, plus root 2 over 2. So that makes it a 2 root 2 over 2, which I think is just minus root 2, if I'm not mistaken. Oh my goodness, yes it is. Okay. So, y-intercept is somewhere down here at minus root 2 over, no, just root 2, which is about 1 minus 1.4. And even in my ugly drawing, that looks reasonable, okay? That could be the negative 1.414 is the y-intercept, slope 2, yeah. Not too bad of an approximation. That first curve would have been miserable. Let me see if I can clean that up a little bit. It's going to mess up the other side dreadfully. But I'm not as worried about the other side because we're over here on this side. So that looks reasonable anyway. Positive slope, slope of 3, and it looks pretty steep, so slope of 3 works. Any questions on that? Make sense? All right. Now, I think we've already hit all the homework assignments, but let me hit them again real quickly. I won't do anything quickly, but any of the odds, 5 through 19, they're all at Calc Chat, 5's at Calc View. Either 21 or 23, they're both at Calc Chat, 23's at Calc View. Any of the odds, 25 to 31, they're all at Calc Chat, 25's at Calc View. Either 33 or 35, they're both at Calc Chat, 31's at Calc, 33's at Calc View. Any of the odds, 37 to 41, they're all at Calc Chat, 39's at Calc view. There's an exploring concepts, implicit and explicit forms, 43. You can do whatever you want to with that. There may be something at Calc Chat. I don't know if there is or not. Excuse me. I would do 45. It should be at Calc Chat. 47 is both a Calc Chat and Calc View. You can do any of the odds, 49 to 53. They're all at Calc Chat. 53 is a Calc View. Do 55. It's a Calc Chat. 57 is a Calc Chat. 59 should be at Calc Chat. 61 should be at Calc Chat. You can do either 63 or 65. They both are at Calc Chat. They kind of throw something in on you. It's nothing new except the terminology, talking about orthogonal trajectories. And what does it mean to be orthogonal? Any ideas? Say again? Perpendicular to each other. So that means their slopes should be perpendicular to each other. Now, dredge back in memory, and what does it mean for two slopes to be perpendicular? What's the rule on that? Negative reciprocals of one another. Exactly. Okay. So both 63 and 65 deal with that, and 67 does as well. Okay. And 69. So you can do any of those, more than one of those, whatever. 69 is showing a topographic map which has isoclines, lines of equal elevation. That's what the cline means. Iso means same elevation. You can see B is a point near the summit of this mountain or hill or whatever it is. A is some point down one slope, and I guess they're asking for something about the trajectory there. I'll let you fiddle with that if you'd like. 71 is finding equations of tangent line like we just did. That should be at Calc Chat. 73 is a proof if you're interested in that. 75 is another tangent line, as is 77. All those should be at Calc Chat. Then there's some special project on optical illusions, if that's really something that you want to spend some time on there. You have that there, I guess, an article, The Mathematics of Optical Illusions, so go for it. Okay, again, I wish we had time for related rates. We don't. Pretty interesting problems. Let me just give you a hint on it. They're talking about just rates to begin with, some rules and definitions. But when you have a problem that it's asked for a rate of change, like in example 2 on page 153, a pebble is dropped into a calm pond causing ripples that form concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. Radius increasing at 1 foot per second. So you can say the rate of change of the radius rate would be, if you have r as a function of t, dr dt would be feet per second. Radius measured in feet, time measured in seconds. When you see feet per second, think that has to be a derivative. dr dt. Okay? That's the big key here. And then you're given a formula that you probably should know already, and then you deal with that. So the guidelines are there. They're fun problems. We just don't have time to go over them. But you can do them on your own if you're really interested. Okay? And they are a lot of fun to do. Review exercises. If you need a few more exercises to do, all these are at Calc Chat. None of them are at Calc View. So you could do either 1 or 3 if you chose, 5 if you chose, 7 if you chose, any of the odds 9 through 19 if you chose, 21 to 23, or 23 if you chose, 25 if you chose, 27, Any of the odds 29 to 39, 41 or 43. Any of the odds 45 to 51, 53. Any of the odds 55 to 65, 67 to 71, 75 to 73 or 75. After that, they're mostly 77 is a related rate problem. If you want to try it, you certainly can. I think 79 to 83 are just implicit differentiation, so you can do those. There's tangent lines given here, then they give you, it sort of irritates me when they do this. Then they give you a new concept in the problem, the normal line. If it was worth doing, you should have it in the section, not in the exercises. And if you want to read on that, it will come up later. But these are pretty much related rates anyway, so I'll let you. Well, 85 isn't, but the rest of them, I think, are. Okay. And then if you're really interested in a problem-solving problem, talking about circles of curvature, you're going to be talking about them later, but not in this course. So if you want to get a jump on it, you can look at that. So finally, we're ready to start Chapter 3, which is applications of differentiation. Even though some of our examples have been giving us, these are more specific. 3.1 is extrema on an interval. And really, we've already come pretty close to doing this as well. Our objectives here, understand. By the way, before I get going, did everyone here get a copy of the test? That I did not? Okay. Let me give you that because I did give them out last time, even though we hadn't quite technically finished the section. And that means, folks, if I don't have your test 1 in, good time to get those in because this is test 2 already. Okay. How many was it? 1, 2? Just 2? Okay. Still one person I haven't given a test to, but I'll get it. Guess they'll show up at some point. Please get, if you haven't already, get your test 1s into these. So you won't have 2 of them ending at the same time. And also, let me just make the comment. This, of course, one of my best classes ever. I've received one research paper. Only one. Oh, I don't know how that happened. Okay, so don't forget that either. We're this close to midterm, folks. Okay, so please get me in. And by the way, right at or after midterm, they usually request midterm progress reports, which means if any students who are failing D or F at midterm, if I have nothing in from you, not a research paper, not your first test, that pretty much averages out to be a 0, which is F at midterm. That doesn't mean too much, except you might just start getting bugged by people. Is there anything we can do for helping and tutoring and advising you and counseling you on stuff? So if you don't want that hassle, get me some stuff in. Your research paper, test 1. Need the test 1 anyway. All right. Objectives for Chapter 3. Understand the definition of extrema and of a function on an interval. Understand the definition of relative extrema of a function on the interval. And find the extrema on a closed interval. Okay. One word separates those first two, relative as opposed to extrema, and then we'll go about finding. So let's talk about what we mean by extrema. What kind of word is extrema anyway? Have you ever used that in normal everyday language? What do we mean by extrema? This is from the Greek. Say again? Yeah, it's a plural word. Extreme, and then I would say extremes. But you see, they use extremum for singular and extrema for plural. That's what that's talking about. The extremes of a function. Okay. But if you make it sound complicated, it's got to be, right? Okay, no mind. Okay. In calculus, much effort is devoted to determining the behavior of a function f on some interval I. Okay? You know, in real life, that's usually the case. My younger brother used to be, he's retired now. He's retired now. I'm older than him. What's wrong with that picture? But anyway, of a vice president of a small rural electric company, and he had to do the calculations at the end of a year, and he would go back 5 years and look at things like, kind of like the related rate type thing. You look at the trends for energy costs, energy usage, customer base, the equipment costs, cost of the electricity for them, income received, all these things. You look back at the previous 5 years and get their trends, and then project for the next year what they were anticipating happening with the company. So would they need to request a rate increase from the state? Okay, that was the whole point of it. So determining the behavior of function on some interval. He was determining these on the last 5 years. 15 years ago isn't going to tell it much now, you know, because everything's changed since then. And neither will just 2 years. That won't be good enough. So 5 was a pretty good compromise, some interval I. So it's not just in calculus. In real life, you usually deal with intervals. Does f have a maximum value on I? That's pretty useful to know, especially if that was a profit curve. If you reach your maximum profit here and everything system was going downhill, you might want to change something, okay? If you're heading toward a maximum, that might be a pretty good thing, but not reaching it. You know, so yeah, there may be value in that. Does it have a minimum value? Well, maybe if you're trying to minimize cost, have you hit that, or is it still ground that you can go to? Okay? Where is the function increasing? Okay? Where is it decreasing? All these are valid questions, and if you think in real life, quite good questions that you'll run into in reality. Okay? In this chapter, you'll learn how derivatives can be used to answer these questions. You'll also see why these questions are important for real-life applications. Now, y'all are probably, some of you are too young to remember this probably, but the big buzz was going on about on Wall Street using derivatives and doing things with derivatives. I thought, have they finally started using calculus in determining something like the stock market? I said, that makes sense, finally, you know. And then I found out it was some sort of scam type thing. They weren't really using them properly or whatever, so I was deflated. But anyway, it seems like to me there'd be some great uses for it. All right, definition of an extreme, or extrema, more than one extreme. Okay. Let F be defined on some interval I containing some point C. So here we have some interval. Somewhere on that interval is the point C. Has to be within I. F of C is a minimum of F, okay? So you have a function here. Here's your interval. That's your domain, your x-axis, okay? Your function's up here somewhere, okay? Or down here, or wherever it happens to be. But it's your y value, remember? F is your f of x is y. So, if it's defined on an interval I containing C, f of C is the minimum of f on C when f of C is less than or equal to every other f value for x in that interval I. Okay? That's what it means to be the minimum. It's a maximum when f of C is greater than or equal to all the other f values for all x's and on the interval I. So if this is the maximum up here, that's nothing else ever comes close, or unless it equals that, that would be fine too. And the minimum down here, nothing else equals that or exceeds, gets less than that. Those are your minimum and maximum. The minimum and maximum of a function on an interval are the extreme values, that's written in English, or extrema in Greek, I think it is. Okay? Unless it's Latin, I don't know either one of them. So, extrema. Extrema is, the singular form of extrema is extremum. And by the way, which is correct? This data shows, or these data show? Writing scientifically. First or second? This data shows, or these data show? Second. Very good guess, okay? All right. Because datum is a singular point. One point. Data is inherently plural. But you read it all the time and see it all the time. The data shows. No, it doesn't. The data show, not the data shows. It sounds like a singular, but it's not. Okay. All right. Enough of that. The extrema of the function on an interval. The minimum and maximum values of the function on an interval are also called the absolute minimum, meaning nothing gets lower than that. They could equal it, but nothing gets lower. And the absolute maximum means they could equal that, but nothing gets above that. Or the other term for it is global minimum or global maximum, meaning nothing exceeds it, either direction. The extrema can occur at interior points or at the endpoints of the interval. And we'll see figure 3.1, hopefully they'll show it. Extrema that occur at the endpoints are called endpoint extrema. Wow, what a clever name. Okay. So, here's the situation. A function need not have a minimum or a maximum on the interval. Wow. Okay. The only, don't leave that one alone for a while. A function need not have a minimum or maximum on an interval. I almost disagree with that. For instance, figures 3.1, okay. Now let's see what they're saying. Got it. Okay, 3.1a and b, you can see that the function f of x equals x squared plus 1 has both a minimum and a maximum on the closed interval -1 to 2. They didn't say what kind of interval. That's where they got away with it. Okay? If it's a closed interval, it's got to have both a minimum and a maximum. Okay? The only thing that you could argue with would be a horizontal line. Every point on there is both a minimum and a maximum. So that was what I was saying. Never mind. Okay. So if it's a closed interval, though, you will. Closed interval includes both endpoints, right? And includes every point in between. Okay? So if this is your function, and by the way, they didn't even say continuous function, they're showing only continuous function. That's okay. Okay? Continuous, but don't assume it's continuous for a while here. This is obviously your minimum, and that's obviously your maximum. Okay? On the interval -1 to 2. And what you do, you have to check every value. Here it certainly is a value, but it's neither max or min. This is a min, that's a max. Now that's just looking at them. We'll actually find that later. Okay? However, if you define this as an open interval, 1 to 2, then it does have a minimum, but because it's an open interval, there is no maximum, because that point's not included. Well, how about the point just before that? Okay? Will you tell me what that is? You tell me a point just this side of 2, I'll find one closer. Anyone you would choose to tell me, I'll find something closer to 2 than that. No, there is no maximum there. And this endpoint's not defined either, but that doesn't matter. There's a min, not a max. So that's why they would say need not have a minimum on an interval if it's an open interval. If it's a closed interval, you got to have, except for the possibility of horizontal lines, you got to have a minimum and a maximum. Okay. Moreover, in this figure, you can see that continuity or lack of it can affect, that's what I was talking about before, the existence of the extrema on the interval. Okay? Bizarre here. What if this just happens not to be defined at this point for x equals 0, but it's defined up here for x equals 0? Then that is no longer a minimum because it's not defined there, okay? That's still a maximum. That goes back to be a maximum because it was defined there, closed interval. But if it's discontinuous, there's no guarantee that you have a maximum in on that interval. Okay? That's the justice theorem below. Okay? Extreme value theorem. If f is continuous, we wiped that possibility out. If f is continuous on a closed interval, we've wiped out those two problems. Okay? Then f has both a minimum and a maximum on the interval. And that minimum and the maximum are either going to occur at an interior point or at one of the endpoints. But it's guaranteed to have both a minimum and a maximum there. Now, they still haven't said anything about what a horizontal line would be. I contend that every point is both a minimum and a maximum. So it does have one, but not a unique one. Okay. But they're leaving that out for now. So, that was all blah, blah, blah. Okay? There is an exploration given at the bottom of page 166. I forgot to bring my watch up. I always do that. Okay? Finding minimum and maximum values, and it's going to explore doing what we do on the next page, so let's just do it on the next page. Relative extrema and critical numbers. Now, quite often I will let it come out critical values. I'm used to that. They say critical numbers. They mean the same thing. Okay? In figure 3.2, that's this one, the graph of f of x equals x cubed minus 3x squared has a relative maximum at the point 0, 0. Now, why do they say relative maximum? What have they not given you here? See, they haven't even defined relative maximum yet. But what have they not given you in this problem so far? The interval. Okay? That's why you can't say anything about it, because you don't know the interval here. Okay? If the interval was from -1 to -2, that would be an absolute maximum. Okay? Because nothing gets higher than that in here. But since they didn't give you an interval, and you see this one just keeps on trucking up here forever, okay, this function, if they don't give you an interval here, this is neither going to have any kind of maximum or minimum, okay, except for the relative kind, which they haven't told you about yet, but they will in a little while. Informally, for a continuous function, you can think of a relative maximum, here it is, as occurring on a hill of the graph, and a relative minimum as occurring in the valley of the graph. This is if it's a continuous function. Yeah, that makes sense, right? The peak, the crest of the hill, the depth of the valley. Okay, that would be your relative minimum or maximum or minimum. Okay, and sure enough, this one looks to be at 0, 0, and at least this figure looks to be at 2, 4. You can plug them in and see that will actually be 0, 0 that you can be pretty confident on just by drawing of a graph. Might have a little question about 2, 4, 2, -4. Okay. So how can we be a little more certain than just how it looks? Such a hill and a valley can occur in two ways. When a hill or a valley is smooth and rounded, the graph has a, guess what? What's true about this maximum point here? What's happening before that?
Increasing.
What?
Increasing.
Yes, it's an increasing function. What is my hand trying to represent here? Now it's up there. tangent line. The tangent line. What is happening to the tangent line? When it's increasing, what's the tangent line? The slope is positive. And when it's decreasing, what can you tell me about the slope of the tangent line? Decreasing. Negative. Well, what's in between positive and negative? Zero. So the slope of the tangent line at the peak or the valley, if it's a smooth continuous function, the slope will be zero. If it's not smooth, one of these pointed or cusps or things like this, no, can't tell. Not easily anyway. Okay? But if it's smooth and continuous, so you can't have any gaps either, no matter how smooth, but that's not very smooth to have a gap in it. Smooth and continuous functions, the slope of the tangent lines are going to be zero at both the max and the min. Make sense? Okay. That's what we're heading toward, and I think that was what the exploration was going to take you. So, they can occur in two ways. When the hill or the valley is smooth and rounded, the graph has a horizontal tangent line, meaning the slope of the tangent line is zero, okay, at the high point or the low point. When the hill or the valley is sharp or peaked, then the graph represents a function that is not differentiable at the high point or the low point. Why would it not be differentiable? The slope of the tangent line, or the first derivative of the function as you approach that point, would be not the same as you approach that point from the left as from the right. If it's pointed, those two slopes are not the same on this side and that side. Okay? If it's cusped, they're not the same. If there's a discontinuity, the function's not even done there. So when the hill or the valley is sharp or peaked, the graph represents a function that is not differentiable at the high or the low points. Okay? So these two things I've already tried to get you thinking of in terms of derivatives. Okay? That's your definition of relative extrema. Relative extrema now. They sort of left absolute extremes in the whatever in the dust. Here's the definition of relative extrema. If there is an open interval, notice there they're not saying closed interval anyway. Open interval containing C on which f of C is a maximum, then f of C is called a relative maximum for f. There's an open interval containing C on which C is a maximum. Now that doesn't say given an open interval. It said if there is any open interval containing C on which is a maximum, then f of C is called a relative maximum of f. In other words, if you have something that's changing real quickly, just a little zigzag here, but it does go down a little ways, up a little way, take your interval and be really small here. And on that interval, that's a relative maximum, that's a relative minimum. Okay? So you can adjust your interval. If there is one, any way adjusted, that would be a maximum or minimum, then you can say those are relative maximum or relative minimum at C, f of C. Now, have you wondered at all? Probably not. Why they use C? Why didn't they use A, B, psi, theta? Why did they pick C? Well, they're going to call these the critical values or critical numbers, and that C starts with, critical starts with C. We're coming to that, just to let you know. If there is an open interval containing C, on what you might say, well, it could be a constant value, it could be, okay. Containing a constant on which alpha C is a minimum, if you adjust that interval such that you can get that to be a minimum value on that very restricted interval, then that's called the relative minimum. And you said that alpha C has a relative minimum at C alpha C. This is x, y, by the way. X is the C, y is alpha C. The plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. Okay. Now, we didn't need to do that when it's absolute, because you wouldn't have a plural. Well, I guess you could, if there were two that had equal values. Here, you certainly could. So this is much more common to see relative maxima and relative minima. I guess you could on the other two. or local extrema, local minimum. So just like we had multiple terms for the absolute or total or whatever they use for relative ones, you could go local maximum minimum or relative maximum. Means the same thing. Okay. Local means you've made that interval so they are local to each other. So find the value of the derivative of each relative extrema shown here. Boy, they're going about this strangely, aren't they? Okay. They've given you the relative maximum. They say find the derivative. So here's your function. F of x is equal to 9x cubed x squared minus 3 over x cubed. How will we find that f prime? What rule are you going to need to invoke? You can do it any one of either of two ways. Which way you want to do it? Quotient rule. I was afraid you were going to say that. Okay, how the quotient rule goes? X cubed low. Okay. Would it help to multiply that out? Is that what you're doing in your head? Distribute that.
So it'd be 18x.
18x, okay. Does everybody see how he got that? Derivative of the numerator is 18x. If you multiply this out, that would be 9x squared minus 27. Minus 27 is not going to contribute anything to the derivative. Only the part with the x in it, so it would be 18x. So yeah, that's it. That's low, d high, minus
9x squared minus 27.
I like that too. But if you're doing that, put it in parentheses. Okay? Because that minus sign is going to change both of those, and then it wouldn't read like you just said. Times 3x squared, that's d low, over, ooh, that's ugly, over x to the 6th, low, x, the denominator squared. All right. So, we got some, the calculus is over with, now it's just the math. So this will be 18x to the 4th minus 27x to the 4th. See what I've done? The minus 9x squared times 3x squared would be minus 27x squared. And you have a minus times a minus, that'll be plus 27 times 3, that would be plus 81x squared. Follow? Over x to the 6th. All right. Now that we've gotten the first derivative, I would definitely factor some things out. In fact, let's make life a little easier and divide out x squared anyway. So that would be 18x squared minus 27. Well, let's just subtract those. Why am I doing that? I'm not being lazy enough here. Okay, 18 minus 27 would be negative 9x to the 4th, and we're going to divide two of them away, so negative 9x squared plus 81 divided by x to the 4th. Just get rid of those extra x squared that you don't, not going to want to calculate anyway. So here we have the value x is equal to 3. No y's in there, so who cares about the 2 for now? So let's plug in and see what happens when x is equal to 3. 3 squared. Nine times 9 is, negative 9 is? Negative 81 plus 81 is? Oh, what a surprise. Okay. 0, and just to make sure, the denominator is not also 0. No. 3 to the 4th power is also 81, by the way, but who cares? 0 over 81. So, wow, the first derivative happens to be 0 there, okay, at your relative maximum. What a surprise, okay? Now, what's your first derivative here, okay? This is a piecewise defined function. Remember, it's x, it's an absolute value function. It's x anytime x is greater than or equal to 0, and it's minus x anytime x is less than 0. Remember? Piecewise defined function. Okay? Now, what's the derivative of L for the, that's ugly. I looked at it there. I see it's hardly readable. Okay. On the first interval there, which happens to be the right-hand interval, what's the first derivative of this? What? What's the first derivative of this? Negative 1. Okay? At 0, 0, what's the derivative? Negative 1 coming in from the left, positive 1 coming in from the right. Does not exist, because for the v, the limit of those two, that doesn't exist, okay? So that does not define, okay? Does not exist. All right? So F prime at 0 does not exist. Okay, over here, a good old sine function. What's your first derivative here? I guess I should write this down. F prime here would then be 1 when x is greater than or equal to 0, and negative 1 when x is less than 0. And so the first derivative doesn't exist at 0. All right? In fact, to keep from, you had every right to argue about that equal sign there. It's okay down there, but not when you take the derivative. Okay? That tells you it would be equal. It's not. Okay, now let's do sine. What's its first derivative? Cosine x. Okay, now let's pick out those. On this interval here, there's only a max, local max and a local min on the interval shown here. It's not the only one. Yeah, but never mind. We weren't worried about that yet. What is the f prime of pi halves? Yeah. No, cosine. F prime of, that's f of pi halves is 1. F prime, second? 0. How about down here? F prime of 3 halves pi. What's it? That's 0 again. Cosine is always 0 at your half pi's. And both of those are half pi's. I like half pi's if I've had the first half, so both of those are 0. Now, this is just 3 examples. But what does it suggest to you? You have a relative max or min whenever the first derivative is either 0 or not defined. That's the only 2 cases where you'll have a relative max or relative min. Not guaranteed you'll have one there, but that's the only 2 times that will happen. Okay? So here they're going to do the same thing we did. They took the derivative and they used the quotient rule too, which is fine, perfectly good rule. That's the low, x cubed, d high, which is 18x, minus high, 9 times x cubed minus 3, d low, which is 3x squared, over low, which is x to the 6th. Y'all skipped some steps they didn't, which is, they factored out, just like we did, the x squared, but then they went ahead and factored out a 9 from the numerator, which I was starting to do, but I thought, what's the point? We're not doing anything else with it. And that gave, at the point 3, 2, the value of the derivative f prime of 3 is, because that is f prime, it would be 0. Okay, because 3 squared is 9, 9 times 9 minus 9 is 0, no matter what it multiplied the other. Okay, we just did 81 minus 81, same deal. Okay. And that was 0 over 81, it didn't matter. So, relative maximum there. First derivative is 0 at the relative maximum. On this one, the x equals 0, the derivative of that does not exist because the following one side of the limits differ. Okay? As x approaches 0 from the left, that's a minus 1. As x approaches 0 from the right, it's a positive 1. Those two limits will never, no matter how close you get to 0, they'll always be, if you to the left of 0, it's negative 1, right of 0, positive 1. Near the twain do meet, and so the limit does not exist. This is, though, cosine x, and at the max and min, which are pi halves and 3 halves pi, cosine is 0 at both of those. So therefore, your first derivatives are 0 at your local max and local min. Relative max or relative min. Note that in example 1, at each of the relative extrema, the derivative is either 0 or doesn't exist. The x values at these special points are called your critical numbers. Also, I call them critical values quite often. So if I say that, I'm meaning the same thing. This illustrates this. This one does not have a derivative at that point. It has a derivative going to the point. That's a, looks like increasingly positive number, but coming down this way, it's a very strong negative number, getting less negative as it goes down. This one probably is going to positive infinity from this side, coming from negative infinity. That's the slope I'm talking about. So it does not exist. That's a critical number. And this one here, horizontal tangent, first derivative is equal to 0. So the first derivative is a test. The values either 0 or not existing. That's what makes it critical numbers. Will all these be max or min? Not necessarily, but every max or min will have either of those two situations. Okay, so here's the definition of a critical number. Let f be defined at some point C. Okay, be defined at C. That means you can't have a hole in the graph with some other definition somewhere else. Can't happen. Okay, so f is defined at C. Oh no, you could have that. It would be defined at C. And if f prime of C is 0, or if it's not differentiable at C, then C is the critical number for f. That's the definition above. The critical number C has to be in the domain of f. Okay? It has to be, f has to be defined at C. It can't be one of these where it's going to a vertical asymptote there. No, those C's will not work. The f is not defined in a vertical asymptote. Okay. But C does not have to be in the domain of f prime. Okay? Well, because f prime may be not defined there. Okay. Theorem 3.2. If f has a relative minimum or a relative maximum at x equals c, then c is a critical point. Okay. Now, notice here, if f prime is 0 or not differentiable at c, then it's a critical number. If F has a relative minimum or maximum at x equals c, then c is a critical number. So that's coming from the derivative side. This is coming from the max or min side. All right. Make sure. All right. A featured artist here, mathematician actually, Pierre de Fermat, trained as a lawyer, actually I believe was a philosopher, and I think perhaps also a theologian, if I remember right. Did not consider himself a mathematician, but he loved math. So much so it was almost a passion of his. He communicated with mathematicians. I think Pascal was a good bud of his and several others. And he wrote many letters and things and claimed to have found some things, but he was not being a mathematician. He wasn't real good about leaving a paper trail, as in proofs and things. But he wrote to someone sort of as a side, oh, and I found this would be interesting, but didn't say how he found it. And to this day, people have been trying to prove some of Fermat's theorems. I think one of them's called Fermat's last theorem, because he died shortly after he wrote the letter, and no one ever got to see the proof that he said he had of it. So anyway, pretty interesting character. He wrote many of the fundamental ideas of calculus long before Newton or Leibniz, and he came up with this theorem, the one that we just had there, 3.2. And there's a little proof here too, so I'll let you see how they go through doing that. Sorry we don't have time to do those for you pure mathematicians who, that's your heart and soul is the proofs of a theorem. All right, so let's find the extrema on a closed interval. Let's just get down to finding it. Theorem 3.2 states that the relative extrema of a function can occur only at the critical numbers of a function. Knowing this, you can use the following guidelines to find the extrema on a closed interval. Okay? Find the extrema of a continuous function f on a closed interval a to b. Use these steps. First, find the critical numbers of f in the open interval a to b. Not the closed, the open. Okay? Now, how do you think you'll find those? Take a derivative, of course. Good answer in Calculus 1 class. Okay. Take a derivative. Okay? Secondly, we'll evaluate f at each of those critical numbers you came up with in a to b. Then, because they said this on a closed interval, you have to go back and evaluate f at the endpoints, at a and at b. Not anything else, just a and b. The least of those values of your critical numbers, okay, the f of the critical numbers and the f at the endpoints, the least of those is your minimum, the greatest is the maximum. Okay? So, this is the extrema. Not relative extrema. These give you relative extrema. If you include the endpoints, then you should have the extrema. Okay. So let's do example 2. What would you do first? You can follow their pattern or you can slightly deviate from their pattern, but you got to do everything in it. What would you do first? Find the extrema. That's a good answer in Cal 1. Take a derivative, f prime of x. And what is that? Okay? All right. Now, what will we do to find the extreme values? The critical numbers. What did you used to do after you had factored a quadratic? Second? Set it equal to 0. Same thing here. Different reason, but here you're interested in finding where the first derivative is 0, horizontal derivative. Okay? One thing you're interested in. So set this equal to 0. What does that yield you? What would you do from there? Yes, you factor just like you would a quadratic. This is greater than a quadratic. Pull out a 12 what? X squared. And what do you have left? X minus 1. And set that equal to 0. And what does that produce? Okay, x equal 1, or anybody? X equals 0. Okay. Now, time out just a moment here. I just want to make a little note here. X equals 0 is actually what we call a double root. That will have a meaning later. You don't have to sweat it right now. But there's actually x equals 0 and x equals 0. I don't know if any of you remember the old Bob Newhart show that this is my brother Daryl, my other brother Daryl. Something like that. But beside the point. You actually have two roots of x equals 0. Not really all that important now, but maybe later. Okay. One root at x equal 1. Okay. So, what you reckon we need to do with those? You found the places where x is equal to 0. I'm sorry, where your slope is equal to 0, your first derivative is equal to 0. That's the relative max or min. But you haven't really found that yet. You just found the x value of that. Guess what you also need to find? The y value, of course. So let's go and plug these two values back in here. F of 0 is equal to, not too hard, 0. And f of 1 is, second, -1. Perfect. Ha! So, right now we have a potential candidate of 0 being a maximum and 1 being a minimum. Okay? We don't know for sure that's going to work, but that's where they are. We know 0 can't be a minimum, and we know 1 can't be a maximum, or the critical values, okay? Because the F values are reversed there, okay? Now, the second question, is there any place where that first derivative is not defined? No. There's a nice polynomial function derivative defined everywhere. So no sweat there. No place where that first derivative is not defined. Not only is the function the polynomial, the derivative is the polynomial. So what? The only two remaining things you have to evaluate. The endpoints. So we also have to do f of -1. That's one endpoint. What would that be? Write out as much as you need to. Anybody? Second? Okay, 3 would be the first term, right? Because -1 to the 4th power is +1. So 3 times 1 is 3. But what happens here? Yes, +4 equals 7. I think 0 just lost its bid for be the max, right? Because this one's way higher than 0. Okay? How about the other endpoint? What happens there? Woo, bigger numbers. What's 2 to the 4th? 16. 3 times 16? And pull out those boxes, okay? 48. All right, then we have a minus, and this will stay a minus because 2 is positive, and cube of positive stays positive, okay? 2 cubed is times 4 is 8 times 4, 32. This winds up being, anybody? 16. Whoops! Minus 1 just lost the possibility of being a relative, or the absolute maximum. We found the absolute maximum, 216, okay? And the minimum? Say again? Nope. Yeah, -1 is less than 7, and 0. So it's be 1, -1. There's your absolute minimum, absolute minimum. There's your absolute maximum. And you really should write them as ordered pairs. Or one way of saying the maximum value on this interval is 16 and the minimum value is -1. But the extrema indicate points, okay? All right. And basically, they say it this way. Minimum and maximum. Which to me is the same as saying this point 1 minus 1 minimum. And this point here, 216 maximum. Okay. Either way you do. The critical numbers of a function need not produce a relative, wait. Doing something else here. Let's let them draw the graph for us, okay? So, begin by differentiating the function, exactly what y'all chose to do. F prime was 12x cubed minus 12x squared. Everybody saw that and saw why, right? Okay. Then, to find the critical numbers, that's the places where the first root is either 0 or not defined. It defined everywhere, so no sweat there. So let's see where it's 0. And just like they did, just like you did, they factored out the 12x squared. That gave you either an x of 0 or an x of 1. Those are your 2 critical numbers, and the only 2 critical numbers, by the way. Okay? Because f prime is defined for all x, you can conclude those are the only critical values. The whole function, not just on this interval, the whole function. Okay? Then by evaluating f at these 2 critical numbers, and you have to throw in the endpoints if you're looking for absolute maximum min, okay, you can determine the maximum value is alpha 2 is 16, and the minimum value alpha 1 is -1. Now, they wrote them this way, and they wrote them in increasing values of your x. So -1 is this endpoint 7, alpha 0 is 0, alpha 1 is -1, alpha 2 is 16. Minimum, maximum. They don't have to be next to each other. In this case, they just happen to be. All right. Now, this is an intermediate value. It's neither minimum or maximum, but this is the input value, -1.7. Going down to 0 here. Now remember we said you had a double root here. Okay? And so that might lend itself. Single root here says that the first derivative is going to change from positive to negative or negative to positive. A single value there. So this will end up having to be either a local or relative maximum or minimum. Okay? It turned out being a local and an absolute minimum. Okay? However, at this point, you had 2, and it's sort of like, this is one way to think of it, here was one coming down this way, but another one coming up this way. It had two zeros. In other words, you have a double first derivative there, meaning it kisses, the first derivative touches but maintains in the same direction. See, this is a negative first derivative coming in, it's zero there, but then goes negative again. So that would be equivalent to the first derivative coming up, hanging around here, and coming back down. And that's exactly what you have happening there. This is neither a relative maximum or relative minimum, but it had a critical value at that point, a critical number at that point. So you have that on this interval, the minimum's here, maximum there, and this point here is neither a local minimum nor a local maximum. It acts like here it's going to be a local minimum, but then it acts from this side like it's going to be a local maximum. So it's a neither local minimum or maximum. That largely stems from the fact you had a double root of your first derivative. I won't say it will always be the case that way, but I think that will usually produce that kind of result. Okay. Said that wasn't super important. They haven't mentioned it. I just brought it up. Now, in that figure, note that the critical number x equals 0 does not yield either a relative minimum or a relative maximum. It's a neither. Now, we're later going to give it another name, but that's for a totally different reason. Okay? Anyone know what that name will be? It'll be a transition point. So that's not because it neither minimum or maximum, though that's the case here, but it has another reason. Okay. We'll get there later. Believe me. All right. This tells you that the converse of 3.2 is not true. 3.2 says if it has a relative maximum or minimum, its first derivative is either going to be 0 or non-defined. It doesn't say that if the first derivative is 0 or undefined, that will be a relative max or min. That's not what theorem 3.2 says. It only is a one-sided argument there. Only an arrow in one direction, not both. In other words, the critical numbers of a function need not produce relative extrema. If you have a relative extrema, it will be a critical number. But just having a critical number does not mean you have a relative extrema. Okay? One-sided. Whoa, goodness gracious, you can't mean it. Ah, there's more. We couldn't go home without more. Okay, so let's do example 3. How are we doing on time? 2 minutes. Well, we'll start there next time, won't we? All right, let me give you some homework exercises in 3.1. Think you can do any of the odds 7 through 11. They're all at Calc Chat, 7's at Calc View. You can do either 13 or 15. They're both at Calc Chat. You can do any of the odds 17 to 21. They're all at Calc Chat, 17's at Calc View. And then you can do any of the odds 23 through 39. They're all at Calc Chat, 25's at Calc View. You can also do either 41 or 43. They're both at Calc Chat. 41's at Calc View. And if you want to, you can play around with 45 or 47. They should both be at Calc Chat. And 49. And 51. And 53. All right, we'll pick up the rest of those later. Good deal. All right, good deal. We'll see you on Wednesday. And for folks who haven't, please get your first test in. And for those who haven't started, get started on your research papers. You don't want the end of the term to catch you with no paper. That usually results in lower scores.